of most of the topics of Laplace transforms have already been recorded, so sometimes I might not record the lecture that I have with you, but just post the link of the same lecture that I had with another class. So you might see that because I already recorded that. There's no point recording the same thing over and over. We can just have a lecture and then I post the link for you guys to watch. It's going to be exactly the same material. Right now we got 12 students and unfortunately 3 minutes into class time, so I have to start. So, like I said, what we are going to be talking about is inverse Laplace transforms. So, definition. So, little f of t is the inverse Laplace transform of capital F of s. By definition, if and only if the Laplace transform of f of t is equal to capital F of s. That's what it means. So technically, this entire lecture is about going backwards from the function capital F of s to recover the function little f of s. The previous lecture was about taking little f of t, computing the integral or using the theorem to find capital F of s. Today we go backwards. So notation is f of t equals inverse Laplace transform of capital F of s. That's how you denote that. Example, let's say, what is the inverse Laplace transform of 1 over s? From last time, what is the function that we define as having Laplace transform equal to 1 over s?
Isn't it little f of t is equal to 1?
1. So that's it. So the inverse Laplace transform of 1 over s is 1 because we found out that the Laplace transform of 1 is 1 over s. That's it. The inverse Laplace transform of 1 over s to the n plus 1 is equal to t to the power n, this time divided by n factorial. Why? Because the Laplace transform of t to the power n, we found it was factorial n divided by s to the power n plus 1. Okay? So technically what we will do today is just going backwards, taking each of the functions that we had on the right, recovering the function that we had on the left, and then use some combinations of those to see how it works out. The inverse Laplace transform of s over s squared plus a squared, tell me what is this? James? What's the inverse Laplace transform of s over s squared plus a squared?
Cosine of AT.
It's cosine of AT. That is because Laplace transform of cosine of AT equals s over s squared plus a squared. And then you got inverse Laplace transform of 1 over s squared plus a squared. What is this one equal to? And say, Ethan? Can everybody see clearly on the board?
I can see it, yes. I'm just having trouble figuring this one out.
Would this one be sine of AT over A?
Yes. So that's 1 over a sine of AT, and that is because the Laplace transform of sine AT is a over s squared plus a squared. Again, you need to know that the most difficult thing in this part will be memorizing the basic Laplace transforms. If you don't memorize them, then you're going to be in trouble. Know what turns into what, forward and backwards. What is the Laplace transform and what's the inverse Laplace transform of these functions? That's why I take time again today to list them both, right? For going forward and then going backwards. So what's the inverse Laplace transform of s over s squared minus a squared? What is this one?
Isn't that hyperbolic cosine of AT?
That's it. And the reason being that the Laplace transform of cosine hyperbolic of AT is s over s squared minus a squared. And then the inverse Laplace transform of 1 over s squared minus a squared. If we look at the other one, what would this one be?
Isn't it hyperbolic sine over A?
That's it. So that's 1 over a sine hyperbolic of AT. And that's because the Laplace transform of sine hyperbolic of AT is a over s squared minus a squared. So that's technically how it works. The inverse Laplace transform of 1 over s minus a, what is this one?
Is that exponential to the AT?
Correct. That's e to the at because the Laplace transform of e to the at is 1 over s minus a. So these are the basic inverse Laplace transforms that you might need. Now, in general, when you're asked to find the inverse Laplace transform, they are not going to be given to you in this simple form. They can be given to you in forms of a polynomial. Therefore, you need to do partial fractions to get the basic formulas that you have here and identify them. So here we say 1. Identifying inverse Laplace transforms. How we do that? Use of partial fractions. Let's say, for example, we have capital F of S equals S squared plus 5 over S cubed plus S squared. And then the question is, find the inverse Laplace transform of F of S. How do you do that? So you look at this and you say, okay, I want to find the partial fractions that will allow me to write this thing as a sum of functions that look like these functions that I have on the left here. So to do so, you got to factor out that denominator. Yes. Was that a question?
No, sir.
Okay, so I was saying to do so, you have to write down, factor out this denominator, find all the factors of the denominator and start writing down the partial fractions. So this S cubed plus S squared is S squared times S plus 1. So you will have partial fractions for S and for S plus 1. Therefore, we can go ahead and say S squared plus 5 over S cubed plus S squared. And then if you remember your partial fractions from your calculus 2 class, you know it's going to be A over S squared plus B over S plus CS, plus C over S plus 1. So you are going to have one coefficient over S squared, another one over S, and another one over S plus 1 because these are powers of S and S plus 1. For a square, you're going to have square, then S. If you had cube, you have cube, then square, then 1. For 1, it's just 1 power. And then you find the common denominator. It's going to be AS. A is going to be A times S plus 1 plus BS times S plus 1 plus C S squared over S squared times S plus 1 equals that, where you can identify now the numerator, S squared plus 5 equals what you have on the right, B times S plus 1 plus BS times S plus 1 plus CS squared. All right, sometimes I like to say them and they say BS, we need to change these notations somehow. Because we are doing differential equations. It's not BS. Is everybody okay? Hello.
Yes.
We good, William. Is he here?
Yes, sir. We're good. Just trying to get it all copied down.
All right.
Why isn't it A times S plus 1 plus
Oh, I
BS?
just swallowed it, Missy. That's A.
Okay, I was confused. Thank you.
Oh, no need to be confused. I got lost. That's one is A, the other one is B. So all we do here is identify the numerators, S squared plus 5 and the numerator of the right. All right, after doing all this, what you need to do is plug in the numbers that allow you to find the coefficients that are here. So if you look at these things, you can see that if we plug in -1, this is going to turn into 0, that's going to turn into 0, and we will find C. If you plug in 0, this turns into 0, that turns into 0, and you find A. Then you plug in any number, and you find B. Is that a good thing? Yes, it is. So that's exactly what you're going to do. So we select the numbers. S equal 0. Put it in. You get 0 plus 5 equals A. Oops, that's it. Plus 0 plus 0. So right away you get A equals 5. 3. Then you plug in S equals -1. -1 squared, it's 1 plus 5 equals 0 plus 0 plus C. Oh, right away, free of charge. C equals 6. Isn't that beautiful? Now you got A and C, and you can plug in any number that you like to find B. And here I'm choose to get in S equal 1. All right, S equal 1. S squared 1 plus 5, 6. 1 plus 5 equals 2A plus 2B plus C. And so that 6 equals 2A. A is 5. 2A is 10 plus 2B, and C is 6. That's it. So the 6 cancel, so you get B equal -5. So now we got A, B's, and C's. And once you get A, B, and C, you get S squared plus 5 over S cubed plus S squared equals 5 over S squared minus 5 over S plus 6 over S plus 1. Therefore, if you want to get the inverse Laplace transform, you just write inverse Laplace transform here. It's going to be inverse Laplace transform of this minus inverse Laplace transform of that plus inverse Laplace transform of this. See? That's how it's done. And now you're going to say this, you get that 5 out, inverse Laplace transform of 1 over S squared minus 5 inverse Laplace transform of 1 over S plus 6 inverse Laplace transform of 1 over S plus 1. And anytime you do this, you end up here with functions that you know that stand right here on the left. 1 over S squared, that will be N equal 1. Is everybody following this? So you look at 1 over S squared, that's 1 over S squared. You come here, 1 over S squared, that's the formula 2 with N equals 1. Therefore, that's T over 1, so that's T. So this thing is equal to 5T minus 5. 1 over S, that's the very first one, that's 1. So this is minus 5 times 1 plus 6 inverse Laplace transform 1 over S plus 1. That's number 7 here, where A is minus 1. So that's e to the minus T. And that's how you do. Looks beautiful to me. Questions? Any questions?
Can you just go over how to do the impartial fraction part again?
Again, do the partial fractions. The first thing you do is factor out the denominator. When you do that here, that's S squared times S plus 1. Each of the factors comes with partial fractions. For S squared, you must have A over S squared plus B over S. For s plus 1, it's just something over s plus 1. After that, you need to find the common denominator, which is s squared times s plus 1, and add the three fractions. When you add them three, let's get a times s plus 1, and the b times s plus 1. Why is that? Because how do you add fractions? You take the denominator of this fraction, you divide this one by it, you get s plus 1. That's why you're multiplying this by s plus 1. Or otherwise, you multiply to make sure you have the same denominator. To have the same denominator, you need to multiply this by s plus 1. You multiply the top by s plus 1. Multiply this by s times s plus 1. Multiply that as well. Multiply that by s squared. Multiply the top as well, and you add them. That's why you will get this same. Does that make sense?
Yes, sir. Thanks.
All right. So that's one of the ways you do that. And once you do that, you can only add them when you have the same denominator. When they have already the same denominators, you just add the numerators. And those are the numerators that you get when you multiply to get the same denominator. Does that make sense?
Yes, sir.
All right, thanks. And then after that, the rest is just art. So you choose the numbers that you plug in to get zeros. Firstly, you choose the numbers that make the coefficient 0. What makes s plus 1 0? It's minus 1, so you use minus 1. What makes s 0? It's 0, so you use 0. When you're done using the numbers that make these common factors 0, you pick any number to find the remaining constants.
Yes, sir. It makes perfect sense.
All right, thanks. And now the rest here is just separating them and using the functions that we have here on the left. Any other questions? Let's look at one another example. So let's say f of s equals s over s squared minus 2s plus let's say not plus, but say minus 3. And so this is the function that we have, and the question again is find f minus 1, the inverse Laplace transform of s. And so here, the steps are same as in the first one. Factor out the denominator. Now let me give you some few minutes. Just factor out that denominator and you tell me what is s squared minus 2s minus 3 equal to. What are the factors?
S minus 3 and s plus 1.
That's correct. Thank you. You are fast. So that's s minus 3 times s plus 1. That's correct. And now what you're going to do, because it's all power 1 and 1, you're going to say that s over s squared minus 2s minus 3 equals a over s minus 3 plus b over s plus 1. No extra powers because each of them was to the power 1. And now you do what we just did in the other one. Bring them to the same denominator. Multiply this one by s plus 1, s plus 1, s minus 3, and add them. So you get s squared minus 2s minus 3. And on top you get a times s plus 1 plus b times s minus 3. So now you set the numerators equal. This equals s. So s equals a times s plus 1 plus b times s minus 3. And then on the next step, you choose the numbers that you plug in to get zeros for some of the coefficients. So what are the numbers that make the coefficient 0 here?
-1 and 3.
Correct. So that's -1 and 3. So you plug in s equal -1. So the left is -1 equals a. Here, this becomes a 0. And so you get b times -4. So you get b equals 1/4 right away. And then you plug in s equals 3. So that is 3 for s equals 3 plus 1 is 4. So a times 4. And then b here, s minus 3 is 0. So right away, you get a equals 3/4. So a is 3/4 and b is 1/4. So you get s over s squared minus 2s minus 3 equals 3/4 1 over s minus 3 plus b, which is 1/4, and s plus 1 over s plus 1. And now you bring the inverse Laplace transforms to both sides. This first one, this is 3/4. What does this one turn into?
Is it e to the 3t?
That's it. Excellent. That's the thing. And then plus 1/4. What is this one?
E to the -t?
That's right. E to -2. And so that's the inverse Laplace transform of that original function. And if you do follow the steps, you would find out that it's pretty straightforward. No complications. You just need to know the basic functions that are there. Now, example 3, where we have things of the second order. So let's say we got 2s minus 1 over s times s squared plus 4. And the question, that's f of s. What is the inverse Laplace transform of f of s? What is it equal to? Now, in this case, you can see it's already factored out. S squared plus 4, you cannot factor it any longer. It's just what it is. It is just enough as is. And so we are going here to say 2s minus 1 over s times s squared plus 4 equals a over s plus. And from calculus, we say that for s squared plus 4, we have a polynomial of degree 1 on top. So that's going to be bs plus c over s squared plus 4. So this is how you would look for the partial fractions in this case. And then again, same thing, common denominator, add the things. Here you're gonna get a s squared plus 4 plus bs plus c times s over s times s squared plus 4. Again, you identify the numerators. You get 2s minus 1 equals a times s squared plus 4 plus bs plus c, and this bs is not Bachelor of Sciences, times s. So that's what you get. And again, you plug in the numbers that make the terms 0. What are numbers you can plug in here? What do you think?
S is equal to 0.
First one is 0, so S equals 0. Life is beautiful. Plug it in here. -1 equals 4a, and the rest is 0. So right away, a equals -1/4. Good. What do we do about the rest? What we plug in next? Right, don't think too much. Usually what I say is just do the same thing. It might sound stupid, but it helps. So plug in the number that is going to make these other parts 0. What makes this part 0? We know that by now already in this class. These are complex numbers, right?
Plus and minus 2i.
Plus minus 2i. So you pick any of them and plug in. Here I'm going to plug in 2i because 2i makes this thing 0. So I'm going to plug in s equal 2i. When I plug in s equal 2i, please follow carefully here to understand what's going on. You can take time to listen and then write it. I give you time to write down. Make sure you understand what's going to go on here now. You get that? One time, perfect. You're going to keep it for forever. 2i, just plug it in and as you plug in any other number. 2i times 2, so that is 4i minus 1 equal. When you plug in 2i, this piece goes to 0, right? That's the reason why we choose it. Plus b times s, that is s is 2i, so that's 2ib plus c times s, which is again 2i. And then we open these parentheses and cross multiply. 2i times 2i, how much is it?
4i squared.
And what is I squared?
-1.
-1. So 2i times 2i is -4, right? So that's why you get -4b. Then plus 2ci. Now here's the magic. This is a complex number. 4i minus 1 equals this other complex number, -4b plus 2ci. When are two complex numbers equal? When their real parts are equal and their imaginary parts are equal. So these two numbers are equal if the real part here, which is -1, is the real part here, which is -4b. So you will have -1 from here equals -4b here. And that's why I'm asking you to listen carefully. It's better to listen in this place than to write. So you solve that, you get b equals 1/4. And you look at the imaginary part. The imaginary part here is 4 equals, the imaginary part here is 2c. So you solve that, you get c equals 2. So plugging in that unique number 2i, you find right away the two constants. You don't need to worry yourself solving systems of equation by plugging in other numbers. If this makes sense, please write down. Are we good? Is everybody finished? You can see we lost one person already. I hope it's not because I use a complex number. All right, let's now see. Continue solving this problem. So we get here for this problem. For this problem, we get 2s minus 1 over s times s squared plus 4 equal a over s. And a is negative 1/4, 1 over s, plus b, that's 1/4 s plus c, 2 over s squared plus 4. So this is what you get when you get to this level. And right there, what you're going to do is do what we just did in the other problem. Split things to obtain what you need. Plus 1/4, I split s over s squared plus 4, and plus 2, and 1 over s squared plus 4. So I split them, and now I can put inverse Laplace transform on them. Inverse Laplace transform of 2s minus 1 over s times s squared plus 4. According to the page, according to this wonderful page, 1 over s is 1. So negative 1/4 times the inverse Laplace transform of 1 over s, which is 1, plus 1/4 s over s squared plus 4. Again, that wonderful page. S over s squared plus a squared, that's cosine. So this is cosine 2t plus 2, and then 1 over s squared plus 4. Again, this page, that is 1 over a, and a is 2, so that's 1/2 sine 2t. And that simplifies to negative 1/4 plus 1/4 cosine 2t plus sine 2t. So that's the inverse Laplace transform in this case. And you can see that if you know that table I gave you on the previous page, everything else is gonna flow. Because when you start, you know where you're going. Any questions? Hello? Ask me any questions. Now let me give you an example on exercises. Exercise. Let's say f of s equals s squared over s squared minus 1 times s squared plus 1. And I give you a hint. Don't try to factor out this one. Just go ahead and do partial fractions with it and use a hyperbolic sign and cosine. 5 minutes, please. Please try to do it. Don't say it's hard and wait for the answer. Let me know when you're ready. Anyone ready to try?
I think I might have it.
All right.
Is it 1/2 hyperbolic sine of t minus 1/2 hyperbolic sine of negative t?
Don't go step by step.
Okay. So for the partial fractions, I got the numerators were s squared equals a times s squared minus 1. And
First write down what the fractions are supposed to be.
so a over s squared minus 1. Oh, I already got it wrong.
On top of a polynomial of degree 2, you got as plus
Yeah,
b.
that's where I
Always.
messed up. Okay.
You might do something else and then still get the right answer, but that's, in general, it's wrong. But, you know, so that's where it starts. And then you go to common denominator, as you were saying. As plus b times s squared plus 1 plus cs plus d times s squared minus 1 equals s squared. That's what you get. And now you plug in the numbers that make these things 0. Here, the numbers are 1 for s squared minus 1. You have 1. When you plug in 1, you get 1 equals 2 times a plus b. When you plug in s equal minus 1, that still makes this part 0. You get 1 minus 1 squared again, 1 equals 2 times minus a plus b. So those are the two equations that you get. And if I want to solve these two, if I add them, the a's cancel. So that gives me 2 on the left. 1 plus 1, 2. A minus a, 0. B plus b, 2b times 2, 4b. So that gives me b equals 1/2. And then if I subtract them, I get 0. 1 minus 1, 0. A minus minus a becomes plus. That's 4a. And then b minus b, they cancel, so I get a equals 0. So in your solution, you just got lucky because actually when we are solving, we get that a is 0. Right? And now for this part, we are going to plug in I, because I is the number that makes s squared plus 1 equal to 0. And I squared is minus 1 equals, this piece is 0, and I get ci plus b times I squared here. That's I squared minus 1 minus 1. So that is equal to minus 2 ci minus 2d. And again, this is a complex number that is equal to -1. So the imaginary part is 0 here, and the imaginary part there is -2c. So you get c equals 0. The real part is -1, and the real part here is -2d. So you get d equals 1/2. So that's it. So you get f of s equals 1/2 1 over s squared minus 1 plus 1/2 1 over s squared plus 1. Because a is 0 and c is 0, that's what you get. And now you get that the inverse Laplace transform of s squared over s squared minus 1, s squared plus 1 equals, this is 1/2, and this one is sine hyperbolic of t plus 1/2, and this is sine of t. That's it. And life is beautiful, we say. Questions? Any questions?
Is there another way to do that? Like that whole problem, is there another way to do it?
I don't know.
Because I did it differently, and I don't know how I still would have came out with that same answer. But I know the way that I did it was wrong.
How did you do it?
Well, what I didn't, when you get the a s plus b, I never did get that. I got the left hand side equal a times s squared plus 1, then b times s squared minus 1. And after doing like what would
That's the
make
same. That's the same thing that the previous person said, and I said you just got lucky at the end that you get the answer, because by solving we get a equals 0 and c equals 0. Otherwise, if they were not 0, you got the wrong answer. Shows that you're lucky in this case that these numbers are 0.
Yeah, I was just making sure, because I was like, I knew that I did it wrong, but I was trying to figure out how it ended up being like that.
Yeah, it's because in this specific case, we ended up with a equals 0 and c equals 0. If they were not zeros, you wouldn't get the right answer. Because technically what you did is the same thing, just that you started by a mistake in your partial fractions, eliminating
Yeah.
a and c, right?
Yeah, I understand where I did it wrong. I was just trying to figure out how it would have came out to be the same answer.
Always for partial fractions, when you have the denominator that is of power 2, you must have a first degree polynomial on top. Okay. Does that answer the question?
Yes, sir.
All right, so that's technically what it is. And you always try to make sure you get that right. Right. So next thing is, if we are able to do this, let me give you one more example before I introduce the next topic that we'll cover next time. One last example to make sure that we are clear on this. Okay, I have a camera that is moving, so I have to move the papers all the time. So exercise, and that's the last exercise for today, and your last exercise from Cameroon. Next one will be from Ohio. So find inverse Laplace transform of s plus 5 over s minus 1 s squared s plus 2 s squared plus 4. Want to find this. So we're going to spend the rest of class on it, right? I give you first 5 minutes to think it over, and then we work it out. First thing first, do the partial fractions. That's it. Any good news? Hello, any good news? Time is running out.
I have the first two variables.
So what's the first step?
The partial fractions.
Mhm.
That's going to be A over S minus 1
Mhm.
plus B over S plus 2
Yep.
plus C S plus D over S squared plus 4.
That's it. That's where it starts. And you always need to think of it like that. Once you have this part, it's like half the problem is out, right? And so we find the common denominator by multiplying by the missing things. So you get A, S plus 2, S squared plus 4, plus B, S minus 1, S squared plus 4, plus here's CS plus D times S minus 1 times S plus 2. So this is what you get, and it's equal to S plus 5. That's the first step. Now in second step, you plug in the numbers that makes the 0. So we can plug in 1 here. We plug in 1, this is 0, that is 0. We get 6 equals 5 times 3, 15A. So you get A equals 2/5 right away. Then you plug in S equal -2 for the second one. So -2 plus 5, that's 3, equals here 0, here 0, and we plug in -2 here. That's going to be -2 squared, 4 plus 4, 8. 8 times -3, that'll be B times 8 times -3, which leads to B equal -1/8. So we got A's and B's. And now for the last guy, we want to find this. So we plug in the number that we make everything else 0, and that only number will be coming from S squared plus 4, and we are taking it to be 2i, because 2i makes this 0 and that 0. And so here we are going to have 2i plus 5 equal 0, 0, and now here. So that is 2ci plus b times, you get s minus 1, that's 2i minus 1. S plus 2, that's 2i plus 2. And then make sure you do the right multiplication here to get the right answer. So that is 2c, so this is 2i plus 5 equal 2ci plus d. And then we multiply these. 2i times 2i, that's -4. 2i times 2, that's 4i. Minus 2i, that's plus 2i. So 4i minus 2i, that's 2i. And then minus 2. Minus 2 from here, and the -4, that's -6. So that's what you get for the first multiplication. Then you multiply again this by that. So this is 2ci times -6, so that's -12, right? -12ci. Then I times I, that's minus 4c, 2 times 2c. And then minus 6d. See that? So minus 6d, and then we multiply here, get plus 2di, plus 2di. And so we can write this as negative 12c plus 2d times I minus 4c minus 6d. And so the imaginary part equals the imaginary part. We get 2d minus 12c equals 2. The real part equals the real part. You get negative 6d minus 4c equals 5. So you get this system to solve for the two numbers. So that first one gives you d equals 1 plus 6c when you solve this one. And so you plug it in here. So that's negative 6 times 1 plus 6c minus 4c equals 5. So that's negative 6 going to the other side. It's 11. 6 times 6, that is 36, and 4, that's 40. Negative 40c equals 11. So c is negative 11 over 40. And d is 1 plus 66 over 40. Which is 20, which is 53 over 20. So that's it. You got A, B, C, D, and now you have your functions. A is 2/5. Inverse Laplace transform of s minus 1, that's e to the t. B is minus 1/8. Inverse Laplace transform e to the minus 2t. Then plus c minus 1140. Yes. Minus 1140. And then s over s squared plus 4, that's cosine of 2t. And then d plus 53 over 20. And then 1 over s squared plus 4, that's 1/2 of sine 2t, just reading the things from the book. And then you get your final answer like that, you get 2/5 e to the t minus 1/8 e to the minus 2t minus 1140 cosine 2t plus 5340 sine 2t. And the goal of this exercise was to get you to work out again the partial fractions. And technically, that's it for me today. I'm not going to add anything else. If you have any questions, you can feel free to ask them. If you don't, I see you in the US next week.
I have